In this screencast, we're going to talk about the applications of using an incline manometer. Not because it just mixes things up from using the standard YouTube manometer, but because it has a practical application. You can imagine that if that right side of that inclined tube was, say, cut open, and we started dragging that tube downwards, all the fluid on the left side would eventually flow out. So you'd have to start tilting that tube up to prevent it from flowing, so it reaches some kind of equilibrium point. Now you can imagine that the further you drag that down, the longer the tube you're going to need. So this means that one of the benefits of an incline manometer is that with slight changes in pressure, you could get very significant readings along that inclined plane. So I've drawn a manometer with specific dimensions here. And I'm curious as to what happens to the level of mercury as pressure on the left side of the fluid increases just slightly, while the pressure reading on the second side stays constant. So specifically, once we figure that out, we'll determine what that change in the reading is when pressure 1 is going to increase by 50 millimeters of mercury. So the first place we want to start is by doing a force balance on both sides. And when we do a force balance in a manometer, it really comes down to just the pressures inside of the system. So we care about the pressure of the fluid that's being measured and the hydrostatic pressure of the fluids inside the manometer. So the difference in pressure between P1 and P2 can be expressed as the following. Now, since we're interested in the weight of the fluid, we're only concerned about the z direction, hence the way I've written this equation. However, we don't have a vertical height of the mercury since it's in an inclined plane, so the value of the height of the mercury will be rewritten as the sine of that theta angle times whatever that length is. In this case, it's 10 centimeters, but for now, we'll just write it as L. Now, there's a number of ways to get to this point. Specifically, what I like doing is to pick two points that have an equal pressure and then set the sides equal. So where the pressure is equal in this system is, let's say, the interface between the water and the mercury on the left side, we could designate PL. If we equilibrate this to the right side, we'll designate the right side pressure as PR. And as I mentioned, that reading on the inclined face difference of mercury is 10 centimeters. So if we start and say that the pressure on the left side must equal the pressure on the right side. So we know that the pressure on the left side must be equal to the pressure at position 1 plus the hydrostatic pressure of the water, which in this case will be the specific weight of the water times the height of the water. Now we know that in this diagram to be 50 centimeters, but I'll go ahead and wait until the end to fill in all our numbers. Now the pressure on the right side must be equal to the pressure at location 2 plus the specific weight of the oil times the height of the oil, which in this case we know is 30 centimeters, plus the specific weight of mercury times the height of the mercury, which as we mentioned before is going to be L sine theta. So we can set the pressure on the left side equal to the pressure on the right side, and when we do that, we get that top equation. Now what we're really interested in is the pressure difference between fluids 1 and 2. So that'd be P1 minus P2. So if I rewrite it in that form, it results in the following expression. So let's answer the first part of this question. What happens to the levels of mercury when P1 increases and P2 stays constant? So you could either look at the mathematical expression and kind of approach this, or we could kind of look at the figure and just understand that as we increase P1, we have to counterbalance that left side force by increasing the amount of weight of fluid on the right side. So the mercury on the left side has to fill more of the tube on the right side, therefore decreasing in height on the left side and increasing in height on the right side. So our reading for an increased pressure is going to move this direction. So we specifically want to determine what that change in that reading is going to be when P1 increases by 50 millimeters of mercury. So there's a number of ways we could approach this. We could first either calculate what the initial pressure difference is given the values in the figure, and then add the 50 millimeters of mercury to it, and then recalculate those values. Or two, we can set up two different sets of equations. One, the following, which is, say, our initial system, and two, what we'll designate as a final system. And what this final system is going to look like, let's say P1 prime minus P2 since it stays constant. And we know that this side of the manometer is going to decrease. So let's specifically say that that decrease in height we'll label as x. And this is going to result in a change y on the right side of the manometer. So for the oil, the specific weight of the oil times the new height, which is going to be the original height of the oil minus y sine theta, since that will be the change in the vertical direction based on the amount of mercury that goes up that tube. So now for the mercury part, still the specific weight of mercury, this time it's going to be L sine theta plus y sine theta plus x, because since we're decreasing the height on the left side by x, we're creating a new equilibrium point. So this height here is also x. So we don't need to do some kind of length times sine there, we just know it's as x. And lastly, we account for the water, so it's the specific weight of the water, and this time it's going to be h, the original height of the fluid, and we're going to add x since we're going to have more weight of the water on the left side. So as I mentioned before, we're curious in what the final minus initial relationship looks like. And once we get that, we can start plugging in our numbers to figure out that change in the reading. So you can see we're going to start with P1 prime minus P1, and the P2's cancel. And you can see now when we look at the oil, that first term is going to cancel. We're going to be left with negative specific weight of oil times y sine theta. And for the mercury, again, that first term cancels. So we'll have negative specific weight of mercury. And this is going to be y sine theta plus x. And for the water term, we'll have minus specific weight of water times x. Again, since that first term will cancel. Now at this point I would always verify my equation, and I could see that I made a pretty significant error and that this should be a positive sign. Since we're looking at the mercury term, it is positive and we're subtracting out that other term. And verifying everything else, it looks okay. So now we have a relationship between the change in pressure on the left side versus these heights x and y. Now unfortunately, we have two unknowns and only one equation, so we need some relationship between x and y. We happen to have the inner diameter of both of those tubes, and so just doing a mass balance of fluid on the left side for mercury and on the right side for mercury, we could figure out the relationship between x and y. Since we're dealing with just one fluid, we know that the mass balance is also going to be equivalent to this case to a volume balance. So if we take the cross-sectional area on the left side and multiply that by the height change, x, and this must be equal to the volumetric change in the right side. Rearranging this, we find that y is going to be equal to 4 times x. And we could plug this directly back into our equation. So you see we have one equation and one unknown because we know what the change in pressure on the left side is. So let's go ahead and start plugging in some numbers and just leave x, the unknown variable, alone. As we begin to put in numbers into our equation to solve for x, we need to determine what system of units we want to keep consistent. And since in the figure we're working with centimeters, it makes sense to kind of go with the SI system, at least in this case for myself. So the left side we have a change in pressure of 50 millimeters of mercury. And we're going to look up in a table the values of the specific weights of the following fluids. Now we're given that the specific gravity for oil is 0.85. And the specific gravity is related to water. So in this case, 9.8 kilonewtons per meter cubed. This is multiplied by the 4x sine theta, which sine of 30 is just 1/2. We're going to add the specific weight of mercury, which is 133 kilonewtons per meter cubed, times 4x 1/2 plus x. And we're going to subtract out water, and we're left with just x as the unknown. When I do the calculations, I get the following numbers, and as you can see on the left side I have kilopascals, and on the right side I have kilonewtons meters cubed times x. Well, in this case, x is a length, and so if we multiply that by the kilonewtons meters cubed, we're left with kilonewtons meters squared, and a newton per meter squared is a pascal, so the units on both sides match up. So when we add up everything on the right side, set it equal to the left side, we get x equals 0.018 meters, or 1.8 centimeters. So we know our value of x, and we could relate it back to our value of y from before. We knew that the relationship of y was equal to 4x. So that means y will equal 7.2 centimeters. So here you can see that even for a very slight change in pressure, just 50 millimeters of mercury, we had a very small change in x on the left side, just 1.6 centimeters. But on the right side, We originally had a reading of 10 centimeters, and we've increased that to a reading of 16.4 centimeters, something that's much easier to read if measuring the pressures. Therefore, reading a change in pressure using the incline manometer is a little bit easier than if it was just a U-tube manometer for very small changes in pressure. Now, you could also recall that the change in the y direction related to the change in x had nothing to do with the fluids and had everything to do with the actual geometry of the system. So you could control that scaling factor using different sized tubes for both the left side and the right side. Something to think about when you're designing your next manometer.